We're underway, audio and video okay? Good. So we survived Machine Week. This is, well, not quite, almost the last new topic. Today's molding and casting. It's going to be compressed. We went 15 over for the machines, and then I can stay for half an hour. Then I have to go off, as I mentioned, to this uh, uh, meeting at NASA headquarters. So I've asked Adrian to finish the last part of class, and I'll show you why in a minute. You're very familiar at this point with 3D printing, probably much less aware of molding and casting. Industrially, this is, at least today, a more important process. And in your lab, in many ways, it's a much more versatile process. So uh, you're going to make a mold and you're going to cast parts in it. And so this was Adrian's homework. If anybody knows Adrian, you know Adrian loves trains. And here's the mold, rigid mold, flexible mold. This is these are various polymers. Here's a candle train, a stone train, and a chocolate train. Let's see, this was an example of, here was a balance bike, and then the tires were made by molding and casting an elastomer to make the wheels. And this was Hank's homework for the all-important job of making molding and casting tempeh. And tempeh doesn't 3D print very well, but you can mold and cast with it. Here's one of the original nice examples. Let's see, this was Alex, wasn't it? Alex Schaub. So here's a foosball table. And so rigid mold, flexible mold, I'll talk about why. And then this is what's called insert molding, where the characters are cast on the arm of the foosball table. And then if you look at the parts, they have good structural properties, a really nice surface finish, and it's easy to do a production run of many of them, all of which is hard with 3D printing. So we're going to make molds and we're going to put parts in them. So there's many kinds of molding. You're probably surrounded by it. Injection molding, something like this, is made by, you heat a plastic and you inject it into a mold. The sprue is where it goes in. The runner is how it gets distributed. The gate goes in the cavity. The vent lets air out. A parting line is where the mold faces fit, and you get a seam there that if it's done well is minimal. And if flashing is, if it's not done well, you have some material leaking between parts of the roll. When it's done well, there's very little flashing. Uh, Insert or over molding is where you cast around a part. So this was Quentin, where instead of making a case for a circuit board, he designed a mold and he just casted right around the part. And that makes it environmentally robust, tough, conformal. It's a nice way to do it. Vacuum molding is where you heat a material, you pull a vacuum around it. That's often used for packaging. You saw roto molding today in one of the machines. Roto molding is you put the material you're going to cast in the mold, and then you tumble the mold on all axes, and that helps you get a smooth shell on the surface of it. What we're going to do is flexible or soft tooling. Here's a great example. So here's a machine controller done for this week's homework. And so to do that, you machine the mold, and I'll talk about that. And then you cast elastomers in it. And to make the colors, he did it in stages. He filled different layers with different colors. And then so he's casting a rigid material and then a flexible material to make this really nicely finished controller. Um, this, this is what's called soft tool. Yeah, this is what's called soft tooling because in a rigid mold, the mold design is much more complex to get your part out of a rigid mold. With a soft mold, you can just bend it out. Once you've done it, then you can crank out parts. This was a student who liked cats, so she designed the mold around it, and then she produced, again, like Adrian, cats in many different materials, and then went into production mode making lots of cats. Uh, so your mold, the simplest is a one-sided mold, and you just get one face. Next is a two-sided mold, but you can go well beyond that. So this, for example, was a six-sided mold. This is a tesseract, a 3D projection of a 4D cube. And you might not think you could mold that, but if you look at the design here, if you can decompose it into faces, you can have a mold on each face. So uh, he made these parts, and then it all comes together in a six-part mold that lets you cast this really complex part. Um, a key task for this week is you need to register the parts of your mold. Often you'll see that done in a way I don't like, where you have posts between the molds that fit. If you look here, this is a demonstration, an example I did that makes a self-inverting top. So it's a top that turns upside down. And a couple things are going on here. So here's the rigid mold, here's the soft mold. Um, you, there's two faces, but if you look, one face completely nests in the other one. So just rather than having a few points of contact, you completely nest one whole mold in the other mold, and that gives you better positional control. And then if you look at the design, I put the parting line right at the seam of the top so you don't notice it's there. And then you need a place to fill the mold, and I'm doing that on the shaft. And then you need a vent for the air to come out. And here's the vent, and what comes out of the mold, there's a little post there that you just snap off and sand down. And so again, you can make rigid molds, but if you make a rigid mold and a rigid part, it's very hard to get your part out. We're using soft, flexible material, but with really good tolerances. And so you can make very complex geometries and just deform to take your part out. There are many vendors. The most important vendor for this week is Smooth-On. Smooth-On has a primary business doing things like making special effect parts for Hollywood. And they have really interesting versions of every kind of material we're using. They're the most relevant vendor for this week. So for the materials, uh, um, there's a few ways you can make the mold. One is by machining and one is by printing, and we'll talk about that towards the end. So we use a low temperature wax. This you can soften. This is good if you want to make an impression of an object and mold from it. This is a rigid wax we use that you can machine to make molds, and then you can melt them down and use it again. Uh, Foam you can machine. It doesn't have good surface tolerance, but it's cheap in large volumes. This is good for making really large molds for things like architectural casting. Alginate, let's see, I don't know if you can hear that. The hotel is testing the fire alarms. We had a note that they're going to be testing their alarms if you hear that in the background. Alginate is a biocompatible material. And so if you want to make, for example, a mold of your face, you can use that. Urethane is one of the most relevant materials for this week. So urethane makes rubbers that are very tough, but good fine detail. And so you can cast from it, deform it, and it snaps right back to the shape. And it also lets you make tough rubber parts if you want. There are urethane plastics that we use, and these in particular are nice because you can tint them with many different colors and fillers. And so you can make plastic parts of just about any color, and you can get all sorts of other textures. For clear casting, this is a nice clear rubber. Um, and then generally we use epoxies if you want to have rigid clear casting. Um, uh, let's see, I'll come back to that when I show the mixing. Um, Silicones can do very high resolution casting. We can do that down to nanometers. And then one of the best materials for this week are these calcium-based compounds. So this is dry stone, hydrostone. They're closely related. Think of this as very high resolution concrete. Dry stone is a calcium sulfate with polymer. Hydrostone is similar, but with Portland cement. It casts at very low cost, very low viscosity. It's very easy to cast in a mold. It gives you a beautiful surface finish. It's very strong in compression. It looks sort of like plastic, but it feels like stone. Um, it's not strong in tension. If you want thin shells or tension beams, it needs reinforcing, but it's good for solid casts and very, very low cost. Um, for metal, most metals are at higher temperatures, but we use an alloy. There's low temp alloys that are soft, high temp ones that are very hard. This is in between. True, you can cast. Oh, actually, I'll come back and tell you about. This is Umu. I'll tell you about. You can cast it. There's a trick, which is you dust the mold with talc, and if you don't do that, you get a poor surface with the metal casting. With it, it helps the metal wet the surface. This is what's called a eutectic, sort of like solder, but much stronger. It's brittle. In a thin shell, it'll snap, but otherwise, it feels like a metal part. It's a killer app is making coins with it. It's not high strength metal, but it's a nice metal casting. I skipped over for silicones. Uh, they're not quite as tough as the urethane rubbers, but these are very friendly. They're very inert. The urethanes and the epoxies need good ventilation. These don't even need good ventilation. They're room safe, and they're very inert. They don't stick to anything. And so Moldstar or Umu silicone with hydrostone and drystone is a really easy to use, versatile casting combination. You can cast ceramics that you mix and then fire. And then this is a really nice series of material that's food safe. And food safety is a bit like being kosher. You have to be food safe at all the steps. So not just the material, but everything that touches it needs to be food safe. But with this, because it's food safety, a killer app for this week is you can make molds and then cast candy, or you saw tempeh, or ice. You can make custom ice cubes with food safe molds. Then there are lots and lots of additives you can use. This is a boat building site. I'm just thinking some examples. You can add glass spheres to reduce density. You can add short fibers that increase the tensile strength. You can add nickel or carbon for conductivity. You can add quartz for thermal conductivity. You can add elastomers. There's actually rubber concrete that's combinations of both. So once you have the base resin, there are all sorts of materials you can cast in it. We'll see more about that when we get to composites. So you're going to make a mold, and we'll talk about that in a minute. And then you're going to pour in the material. That's surprisingly subtle. So the first issue is this is a messy process. It's good to cover it with paper. You should wear gloves, even for the materials that there's no safety issues. It's just sticky and messy. Um, a lab coat is a good idea. And then you want to work cleanly. So this is really annoying. This is somebody mixing and they got the resin all over the bottle. And if you do this poorly, you actually mix the resin and you seal the bottle shut. You need to be really disciplined about just keeping the workspace clean. Once you pick your resin, it has a shelf life and you need to learn how to mix it. So before you make your whole mold, it's important to do test casts. Just cast a little bit of resin to make sure it's working okay. Now, mixing is surprisingly subtle. So here's a whole sequence with one of the silicones. So some of these are by weight. The ones we tend to use are by volume. So you take an equal amount of each. You first stir the container to make sure it's fully mixed in the container. Then we're going to pour equal amounts of each. Then it's poured in. Now here comes a key step. When you stir, you don't scoop, because if you scoop, you're driving air in, and air makes bubbles, and that's one of the banes of this week. So the stirring is shearing, not scooping. So you shear to stir, you scrape around the edges to make sure you're getting everything. And this goes longer than you think. It's quite a few minutes. When you start, it's striated. You keep going until there's no striation, until it's uniform. Then you don't dump it in the mold. You pour it in a thin bead. That helps it flow in the mold. It helps get rid of the bubbles, and you let that flow in. Then at that point, um, the curing time is based on the material. Many of these cure overnight by the specification, but you can make it go much faster just by slightly warming it. It's similar to like bread rising. And so if you use, for example, a thermal lamp or just a warm place, don't put it in a food oven, but you can have an oven in your lab that's not for food. Something like this, in about an hour, you can demold it. And then you get this beautiful mold with all of the fine detail when everything goes well. Um, so the one of the main challenges this week is bubbles. So if you mix it by scooping, you drive in air. If you dump it in the mold, you drive in air. Um, and so there are many different ways you drive in bubbles that then get trapped in the mold. If you do everything right this week, you have a beautiful, smooth, featureless mold. So there are multiple ways we prevent bubbles. One is by stirring by shearing. One is by pouring in a thin bead. One is by, you can vibrate the mold. One is by painting. What you do is, if you have fine features in your mold, you actually take a brush or a stick and you paint the resin on the surface. You make a smooth layer of resin. Then when you pour the rest in, it's flowing resin on resin, and that sticks together much better. And so painting the surface in the mold is a good way to do it. A vacuum chamber pulls the air out. That's a common tool when you're molding and casting. A pressure chamber, for some materials, you can do the opposite and you can force the air in, are both options to do it. And also just time. The So yeah, Patrick, you mentioned both vacuum and pressure, but I'm covering. If you do the stirring and pouring carefully, you don't need a vacuum pot. The vacuum is a shortcut to it. The other note is time. Mixing takes longer than you think, and then when everything is done, bubbles will be coming out of the mold, and if you rush, they get trapped. And so let the bubbles come out. You can scrape them off. Then wait a little bit longer. Let them come out. Wait a little bit longer. Bubbles can also be a sign of just rushing. So you've mixed it. You've poured it in the mold. Uh, then it's going to cure. And so there's a lot of different things going on. There's a polymerization reaction. Molecules are cross-linking. The calcium, the sort of concrete-like materials, are hydrating. Generally, there's a balance of both endothermic and exothermic. Endothermic is you need energy to drive the reaction. And so not all, most of these like being warmed. The the concrete-like materials don't need it. Most of the polymers cure faster and better with a little bit of warming. But then almost all of these are exothermic, which means they release heat. And that has a couple implications. One is when you mix it, depending on the material, over about a half an hour, it gets warm and then it cools off. That's a good sign that everything is working properly. Two things can go wrong. If you mix poorly, it doesn't get warm, and it's a sign you mixed it poorly. And that's really bad because if it's partially mixed, it doesn't cure all the way, but it doesn't stay separate. And you get a gooey, sticky mess that just ruins the mold. The other thing is these are what are called deep cure materials, that they cure chemically, not on the surface, but all the way through. So if you make a really deep section, it gets hot. And so when you pour a giant concrete structure, they can spend weeks cooling it. Here, if you make a really deep section, you have to manage the heat, otherwise it gets too hot. There's a really bad failure mode where you mix too much and then it overheats and it melts the container and you have sort of hot, gooey, melted stuff. And there's not much you can do about that. So deep sections, you probably won't get to that this week. You need to worry about managing the heat. For a smaller mold, the heat is good feedback to show you the progress of it. So then we're going to demold. So again, if you have a rigid mold and you have a vertical face, it's very hard to get out a rigid part. So Lego bricks, for example, slightly angle the faces. That's called a draft angle. And what that's doing is if you slightly angle it, you can then lift a part out. So if you want to cast a rigid part in a rigid mold, you need a draft angle. Again, this week we're doing rigid to soft to rigid that's much more forgiving. With a soft mold, you can have overhang, you can have all sorts of complex features that make it easy to get out. Now, some of the mold casting material stick to some of the molding material. Hydrostone and silicone, for example, never stick. The urethane and the silicone don't stick, but a urethane rubber with a urethane plastic will stick, and you can't get it out. And so for that, you need a release agent. You can buy these release agents that help prevent that, but those are easy to do DIY. A dilute dish soap, for example, is a good release agent. The materials need to be stored sealed. When you buy them unopened, there's a shelf life that's maybe a year or so. Again, except for the concrete-like materials, which last forever. And then when you open it, there's a much shorter shelf life. The resins, a week or two is about the most after you open it, and it's still usable. The concrete-like materials absorb moisture unless you keep them sealed. And so again, that's why it's so important to test the materials. Pick the mold material, the resin, and just make little test casts to make sure it casts properly. Now, for this week, for safety, some of the material have a statement like this: caution, not for home use. That's very, very serious. there was somebody in the Fab Lab in Barcelona who ignored that. He ended up in the hospital. And it's worse than that. He's been sensitized. His body chemistry has changed. So he's now has an allergic reaction to materials in his family. We don't use materials like this ever in the lab. To use these, you need to use them in a fume hood. You need to wear serious protective equipment. All the materials we're using have safety data sheets. Don't do any molding and casting without reading the safety data sheet. I had a neighbor who bought a clear epoxy for projects with her young kids and wasn't aware of this, and so she was using these epoxies in an unventilated space with young children. Uh, there are low volatile epoxies we use that you can use indoors. Most of them need really good ventilation. So read the safety data sheet. Never use a material without checking that. Almost most so silicone, hydrostone, drystone is completely office safe. Everything else needs good ventilation, good airflow around it. Even the non-hazardous materials, again, they're going to be hard to get off you or clothing, so you need to wear just protection so it doesn't get in you. If there's any risk of splashing, you should wear glasses. And then finally, when you're done, you don't just toss these in the trash or dump them down the sink. Any unused resins, you need to cast them so that they become inert. We've actually had people dump the concrete-based materials down the drain where they set and they cast in the pipe. You need to set the material so that it's safe to dispose. Okay, so now let me summarize what's left, and then we're up to the time where I'm going to have to hand off to Adrian. So in the past, everybody machined this week. They would machine the mold, and this was a good introduction to 3-axis machining with smooth surface finish. Increasingly, 3D printers can compete with that, and so you can also 3D print the mold. But in this week's assignment, you're going to design a mold, and then the task is to produce it with a smooth surface finish that doesn't show the production process. So for machining, it's a smooth machining path. For 3D printing on a high resolution stereolithography printer, it has a beautiful surface finish. If you want to use an FDM printer for this week, you need to post-process it. And Adrian will cover this. You need to fill in the surface of the FDM printing so you can't see the roads of the printer. The goal for this week is to make parts that are featureless, that have just a beautiful, smooth surface finish. So Adrian will walk you through options for both printing and machining. I'll show one last thing before I go. This is one of my favorites. This was a self-inverting top that looks symmetrical, but you can only spin it in one direction. And it's a great example of how featureless molding and casting should look at the end. So Adrian will walk you through both printing, machining, software options, and talk through the assignment in more detail. This is one of the most creative weeks. You can design really interesting molds, and then you can work in a wide range of materials that opens up a whole universe far beyond what you can just do with a 3D printer. So with that, then we do have where are we? Luciana is going to host a Monday recitation where you're going to meet the whole ecosystem of the Fab Academy, of the Academy, and I'll explain the relationship between Academy that grew out of Fab Academy. And then as usual, Saturday open time, a little bit of catch up for some of you on your machines, the fun molding assignment, and then the rapid push on the final projects. So with that, I'm going to make Adrian the host now.
Okay.
Okay. So Adrian is the host, and I'll leave you in his capable hands for the last half hour. And I'll see you for the recitation on education, and then I look forward to seeing your molds. So, and once again, great work on the machines from so many of you. Each year the machines really do get better. Okay, I'm off to NASA, and I'll see you in a week.
Okay, thank you,
Bye
Neil.
bye.
Enjoy. Bye.
Thank you.
Okay, we continue. Okay, Neil explains about the here in the safety. Remember the ventilation is important. Use the face masks. Be careful with the gloves because you need sometimes you need to use nitrile gloves. Okay. Okay, about the 3D printing, if you see, you have the FDM process. Okay, this is an example from the Valley from the last year. They use this, but it's a recommendation, a post-processing of this 3D printed. Okay, and if you remember in the class, in the 3D printing class, we have here this processing. Okay, here. From the smooth on this product that you can put in the 3D printed part, okay, and you have a very good resolution, okay. Here, then we have the SLA, okay, during the bootcamp in León in 2024, okay. Pablo document all the process with the LEGU, with the 3D printer SLA, okay? And you have all the resources here. And this is the result of making molds with a 3D printer, okay? This is a wax mold, okay? In my case, it's my little train. And Pablo replicate with the SLA printer, okay? You need to be careful with the curing, okay? Because there are different problems with the curing, okay? When you finish the mold, okay? You can see the different result with acrylic varnish for the release film, okay? Or, for example, here there are more iteration with alcohol, the cleaning, okay? And you can see the results, okay? But be careful with this because sometimes you need to check the components of the release and the components of the silicones, okay? Then is an example of tooling here with Formlabs. There are different resins printers you can use for making molding, okay? And you can see this video. And the speed, there is another video here with explaining the 3D printed molds, okay? And for injection molding, okay? And you have from Formlabs different printers that you can make molding 3D molds more faster than milling the wax, okay? For machining, okay? For machining, you need a surface finish, okay? And always we use, this is my documentation, always we use the wax, okay? Milling the wax. For machining, Neil shows the link of the computer control machining. And here at the bottom, Neil explains the 2D design, okay, and 3D design, okay, but we cover in a few moments. The surface finish is important, okay, and in the surface finish, this is the sample that Neil shows in the class, in the last minutes. Is an example of making an spinner, okay? And you have the wax, the wax here. You can mill it with the softboard or with the Modela, for example, or the Lani. And here you have the result, okay? The surface finish, and you have the perfect finish of this molding, okay? This is the sample to mix in the silicone rubber, okay? And this is the result of the curing the silicone. We recommend to you to make an offset around the mold to retire the silicone, okay? Because sometimes you have troubles to retire the silicone inside of this mold, okay? Here is the silicone, the rubber negative, okay? And this is the casting, okay? The casting, in this case, is with dry stone, okay? And this is the final result. It's an spinner, and here you have the example with the video of the spinner of this result, okay? For this reason, this is a surface finish. If you see here, the result of the milling of the walls, okay? How you can make this surface finish, okay? Well, we have 2 steps, okay? We have the roof part, okay? Now I explain with the sketch pad to drawing, okay? This is the marks, the wax, okay? And you milling with different tool types, okay? One is you can use the flat end for this part. And if you see, this is a flat end and you have different scalloons here and you can see the steps of this result, okay? Then we use the ball end, okay, or the bull nose. For this reason, if you see, we have another finish step over. It's important the step over, and with the controlling modes or the flat can, you can control the step over to milling, okay. And this is the finished part with a 0.1 step over in this axis, okay. But if you milling again in the other axis, okay, you have the finished part and the result here, okay? This is the good idea, okay? In between of this to this, you have to spend more time, okay? In my case, I 45 minutes to milling in the roof part, okay? And then I milling in 2 hours the finished part, okay? This is the result of the finished part. And this is the part I tell about to retire the silicone better, okay? With this offset to retire, okay? Be careful with the tool types, okay? Because you need to use the extra long, okay? Or the tapered end mills, okay? I'm going to cover here, okay? If you have here the wax, okay, and you have here your 3D design, okay, you have the collet, and here you have the end mill, okay. This long size of this end mill, you need to be careful and test it because you can collide in this part, okay, when you go down with the end mill and collide the collet to the wax mold, okay? For this reason, you need to measure, be careful the length of your tool and this distance between the bottom of the mold and the top of the mold, okay? Sometimes you can make, oops, sorry. Okay, sometimes you can make the mold in this case, for example, okay, this is the wax mold. And when you go with the collet and the end mill, you can down around this part, okay? And you don't have the collision with the collet and in this part, okay? Okay. For this reason, you need to make the strategies, okay? And the strategies here is the same that in the computer control machining about the 3D milling, okay? Here in this part, okay? Neil explained the different, because in this case, you mill in 2D, okay? You go 2D, but in this case, you with the finished part, you start in a 3D milling, okay? be careful with the collet, okay, and the collision, okay. You can simulate these strategies with the different programs, okay. Okay. When you milling, okay, here, sometimes you have trouble with the design, okay, because if you have 2 millimeters mill and you have another mill with different size, you have troubles, okay, and I didn't finish this mold, okay. And another little thing is this wax, okay, you can recycle, okay. I remember Gianni every year recycle the chips of the wax and melt it, and you can make another wall max, okay. Okay, here with the software, okay. The software, you can use the softboard, the VCarve, okay. But we have the MOX. Remember, we have the MOX Community Edition. Inside of here, you can find the 3D molding here, okay? SRM or the G-code generic is here, okay, for milling, okay? You need to make an STL file to send to mods, okay? And here Neil has 2 samples, okay, with the roof strategy, okay? You need to upload the file, okay? It's a Rhino. And then you need to be careful with the tool diameter, okay? Remember, it's a ball nose. The offset number, this is important. If you see here, we don't have offset, okay? But here we have offset number, okay? In between the half of the end mill. I continue here. You calculate, and you can see the 3D model of the result. Okay, and this is the G code that you can send to the machine. And you can see here the roof part, okay, the strategy of the roof part, and you can calculate. Here, this is the roof, and here we have the finish, okay. And with the finish, is the same program, okay, but you change the parameters. In this case, here you have to both direction, okay? If you see, you have the SC and YC, okay? You need to long time to calculate this result, okay? And here you can see the result of the milling in both directions. For this reason, it's a 3D milling, okay? Here you can see the result, okay? Okay. You can use Fusion for milling. Inside this Fusion 360 CAM is another system to create the tool paths, okay? Here, this is the part of the assignment, okay? And now we cover the group assignment, okay? Remember, we have 2 parts of this assignment. We have the group assignment. It's important to review the data sheet of the different materials are you going to use, okay? The silicones or the resins, okay? And we always recommend to create a data sheet of document of all of your resins and silicons, okay, in the lab. And you need to, for example, create a little mixing in a cup, okay? And you can mix in. Remember, sometimes you need to use protection, the safety rules, okay? The ventilation, okay? The food safe, you can read the data sheet of the food safes. It's important to understand the put life, okay? The put life is when you missing the silicone, okay? You have only 30 minutes to cover your mold, okay? And you can cure in 24 hours, okay? Sometimes of these different silicones, sometimes you need to cure more with a oven, okay? You need to understand the mix ratio, okay? Sometimes it's the width of the volume, okay? It's 100 part to 10 part of the mix. If you see, sometimes in the smooth on or different resins or silicones have two bottles, okay? And you need to have the part A and part B, okay? And you need to mix the ratio very carefully, okay? Sometimes it's a post-curing, okay? In this case, for example, to expose the rubber 100 degrees for 4 hours in a oven, for example, okay? And the resins, be careful with the resins because that Neil explains, sometimes you have an exothermic reaction, okay? It's hot. Be careful when you put the resin in the table or near the computer or something similar because you have a exothermic reaction, okay? Be careful with this, okay? And yeah, you need to design the mold. And here you need to measure the volume of the mold. Sometimes you can measure with rice or with water, the volume, okay? And this is, please take a photo of you with the safety rules in your lab, okay? And measure, be careful with the property, the parts, okay? And here I continue with the group assignment, okay? The individual assignment, you need to design a mold around the process. You can use the SLA resin printers, okay? But we recommend to you, if you didn't mill in with the 3D model in this week, cover this in the wildcard week, okay? Produce a smooth surface finish. Remember, if you want to use the FDM 3D printer, you need to post-process with this type of products, okay? Use a cast parts, okay? Different cast parts. For example, if you use food safe, you can create chocolates or ice cream or whatever you want. And an extra credit is to make a mold of 2 parts, okay? 2 parts, if you see here, I have 1 part here, 1 part in another one. I use the release mold for this. I cover with the silicone, and this is the silicone with Vitaflex, okay? And I have here the 2 molds part, okay? Here I have the registers, okay? If you see in the first part of the class, I recommend to connect between the molds, the 2 molds, okay? This is bumpers, and sometimes it didn't work very properly, okay? And this is, for example, the food safe silicone, okay? This is the result. And sometimes you need to use elastic bands to cover, okay, the 2 parts molds, okay? One of the holes is for pouring, okay, the resin, and the other is for ventilation, okay? It depends on your type of mold. Be careful where you put the ventilation, okay? And this is the result. Sometimes you have to post-process the result of the mold, okay? But for example, here you can see the result. You can use powder gloves in the dark, okay? And you can make this, okay? Here is with candle wax, okay? You can use make your own candles, okay? Remember, this is a week to discover and research different materials, okay? And you can use the different silicone molds around the week, okay? This is the candle wax, and I melted chocolate with remember food safe silicone, okay? Don't use another silicone, is not for food safe, okay? And this is the result of the chocolate. This is another try to plastic contract. And this is the conclusion, okay? You need to cover You need to start with a rigid mold, okay? In this case, it's a wax mold. Then you have a silicone mold, okay? This is the negative. And this is the result of using this silicone mold. You have the different resins, okay? Wax, or if you use chocolate, you use, sorry, silicone, food safe silicone, you can make a chocolate, okay? This is all the assignment. I don't know if you have questions, comments. I see in the chat a lot of people. Yeah, be careful with the lattice walls. That Rico says some people are allergic. Yeah, I don't know if someone have questions, comments. Thank you for my drawings. Oh, Yanni, 10 years of wax. Amazing. Yeah. The tip that Rico put is you need to spend more time to milling, okay? If you make something bigger, okay? In my case, this is the result. This is the size, okay? You see, I spent more than 3 hours, okay? For this reason, it's a good idea to use the time very well, okay? And if you are more than 1 or 2 students in the lab, remember you need to mill all, okay? Questions, comments? Yeah, to melt the wax is similar than here. I use this little thing, okay, put with water, and you can melt it, and you can then put in a recipient, okay. Questions, comments? If not, we can finish. Oh, Jacob, yeah, Jacob, here. I started, go to the top, okay. This is my inspiration, okay. I need to design the 3D train, okay? And I make 2 parts, okay? In the middle, in this case, I want to make a 2 parts mold, okay? I cut in the middle of the train and I make 2 parts of the train, okay? This is the little, if you see here, this is the little part that I tell you to retire the silicone, okay, inside. Okay, I'm milling, okay? And when I'm milling, I have, this is the positive here, okay? I'm milling, I have the result, and then I'm going to make the negative with a silicone rubber, okay? I want to make the silicone mold here. Remember to use the release mold here. I cover, and I finally have the result of the silicone. And here you have the negative of this train, okay? And then I cover with a resin, okay, here. I create the resin. I put the resin inside of the silicone mold, and I have the positive train, okay? Okay, you understand. Yeah, it's 3 phases, three parts, okay? If you see here at the bottom, I open this bigger, it's better. Here is the first mold, okay? It's a rigid mold, okay? Then I have the silicone mold, and this is the result, okay? Okay, Daniel is, yeah, with the SRAM 20, you can use for walks, okay? And there is a module with mods, okay, of the community edition to make the, yeah, with ball and mill is the best idea. If you see here, I'm going to put in the camera. Okay, you see the ball more or less. Sorry. Yeah, okay. No, it's not, Kai, it's not necessary. You can compare if you want, but it is not necessary. If you go with the, if you see in the group assignment here, oops, I closed the wrong page. Sorry. Molding and casting, yeah. If you see at the bottom, okay, compare the mold making processes. If you want, you can try, okay, but it's not necessary, okay. If not, you can see in the assessment team, the document. Okay, questions, comments? Yeah, thank you, Sahim, for put the mods. And I remember Chris from Alto make a very good videos in YouTube about using the mods and the SRM 20.
Has never registered Face ID on it.
Okay, remember in Saturday we have the global open time, okay, at 10 a.m. Boston time, okay, and we have in Monday with Luciana about the recitation about education. We cover the Academy, all the programs we have in Academy, the Fab Academy, Bio Academy, the Fab Future, the Fab Learning Academy, okay. And it's a good idea to cover this recitation, okay. Flexi mode. Okay, Vicky, but you don't have the silicone to make a, you can talk if you want.
Yeah, currently we don't. We had it on back order and it just hasn't come in.
Oh, yeah. I remember one of the students here in FALab León uses. I need to cover in 2021 students. Lorena. Okay, Lorena. He uses.
Maybe
sorry.
for an emergency trick. Should I? Yes.
Just a moment.
So if you use
I don't see who is talking. Lorena is here making bio silicone, okay, here, Vicky, and you can try. I copied this and put in the chat, okay.
Okay, thank you. Yeah, I wasn't sure if able to test a hard one versus soft and
Yeah. You can try this, okay?
okay, thank you.
You're welcome. I think someone from Ilme now want to say something.
Yeah, I will tell you two of my favorite recipes. One of them is to use just regular silicone that you would use for your bathroom. It used to be cheap. It was like 250 for 330 grams. Now it's 8 euros here in Germany. But if you mix it with 1/3 of cornstarch or potato starch, then you get a material that is very smelly. It smells of vinegar, and it's not pourable, but you can smear it onto things and it becomes like the rubber from your sneakers. It's a fantastic material for many things. And my absolute favorite is a mixture of gelatin and glycerin. So you take, and now it's for the very first time a volumetric measurement. You take 1 shot glass of ground up animal gelatin, comes as a powder. You add 3 cups of water and you heat this up in a microwave so you don't burn it accidentally. And you stir it and you can wash the glass with one shot glass of glycerine. So one of the gelatin, 1 of the glycerine, and 3 of water. And this mixture, if the first time you heat it up, don't boil it, but heat it up so that it dissolves. It won't dissolve perfectly, but what you're left with is very similar to umu. And you can just put it back in the microwave for making it liquid again. Just my absolute favorite. And it's food safe.
Oh, thank you, Ferdi. Yeah. Vicky, here you can find the recipe here, okay? You can follow the steps that Lorena made it.
Thank you.
Okay. Hank?
It's so the biggest problem with biosilicone, so I also like it. The biggest problem with biosilicone is that you cannot cast almost anything in it, because casting mostly involves 2 components. So it's heating up in order to become hard, to harden out. And the biosilicone, I think it's around 28, 30 degrees, and then it starts melting.
Okay.
If you deep frost your mold, you can. I successfully casted chocolate in the gelatin mold, and if you use the trick, the hardware store silicone, make your fingers wet and soapy so it doesn't stick to you. And if you wait a little bit, it will get less sticky, and it dries in 2 hours in any thickness, which is awesome.
Okay, I'm all in favor of bioplastics, so buy it.
Okay, well, remember, this is the assignment for this week. You have 2 parts, the group assignment, individual assignment. Enjoy the molding and casting week. Remember, we have the global open time in Saturday. And in Monday, we have the recitation about the education. Remember, document as you go, and see you on Monday in the recitation and the results in next Wednesday. Bye-bye.
Adiós.
Hasta
Adiós.
luego, entrenadores.
Bye bye.
Bye bye.
Hasta luego.
Gracias.
Delicious.
Adiós, nos vemos.
Ahí está.